Up until now, we've been assuming that there's no external forces disturbing our second order system, whether that's a mass hanging on a spring or an RLC circuit. But that's not very realistic, and furthermore, the most important applications of these kind of systems actually involve external forces. So let's see how external forces show up when we're considering this kind of system. So we have two systems to think about, the mass spring system and the circuit system. So for the mass spring system, let's add an external force. So there's just some external force that's a function of time that's pushing on this mass. And let's take this into account. So remember, we got our differential equation for this system just by writing down all of the forces involved and then using Newton's second law. So the forces involved are now this external force. There's this spring force, which is minus ky. And then there is the damping force, which is minus beta y prime, assuming it's an inertial damping. Now we can use Newton's second law. So Newton's second law says the sum of forces is equal to mass times acceleration. So mass times acceleration is y double prime in this situation. We're assuming that this mass is moving only in one direction. So mass times acceleration is equal to the sum of forces. So that's F of t minus ky minus beta y double prime. And then, as usual, we can move the y and I'm sorry, this should be y prime, not y double prime. As usual, we can move the all the y terms, the y and y prime term, to the right, and we get m times y double prime plus beta times y prime plus k times y equals f of t. So we see in this case, this external force really just shows up as an inhomogeneous term in our second order linear constant coefficient differential equation. And we do have tools for solving inhomogeneous second order linear differential equations, so we should be able to handle this scenario. So now let's look at how this works out in the circuit situation. So in the circuit situation, what plays the role of an external force is an impressed voltage. So up till now, we've been assuming that there's no external voltage pushing this circuit around. But now we're going to assume there is an external voltage, and we're going to call that E of t. For some reason, E gets used for voltage sometimes rather than V. And I think that's just to avoid confusion with the unit of a volt. So we have some external voltage attached to this circuit. In applications, this is typically something like a signal source, like a wire terminal or an antenna or something like that. Okay, so one of Kirchhoff's circuit laws says that the impressed voltage on a loop is equal to the sum of voltage drops around the loop. The impressed voltage now, it used to be 0, but now it's this function E of t. So E of t is equal to, and now we just write down all of the voltage drops across each component. So the voltage drop across the inductor is the inductance times the second time derivative of charge on the capacitor. Remember, Q is charge on the capacitor here. The voltage drop across the resistor is the resistance times the current through the resistor, which is Q prime. And the voltage drop across the capacitor is 1 over the capacitance times the charge on the capacitor. Okay, you can see in both of these situations, this external forcing that's happening really just shows up as an inhomogeneous term. So we can analyze both of these situations just by asking ourselves, what happens when we have an inhomogeneous term in our second order constant coefficient linear differential equation? So to have a look at that, let's suppose we have such an equation. So I have this set up so that it sort of represents any second order linear differential constant coefficient differential equation, notice that there's no leading coefficient here. So, if you start with an actual mass or mass spring or circuit system, you'd want to divide by whatever this leading coefficient is if you wanted to match up with this template that I have here. So we can solve this differential equation just to see what sort of thing happens. Of course, solving this sort of differential equation, to get a particular solution, we'll need to somehow use this forcing function. And in applications, this forcing function tends to be something that we can use undetermined coefficients with. So only rarely would you need to use variation of parameters in this kind of situation. So in this situation, we know that we know a couple things. So first of all, lambda is, in the spring mass situation, it's beta over m, beta over 2m, I guess. And in the circuit situation, it's resistance over 2 times inductance. Okay, and in applications, right, beta represents friction, and so in applications, beta is never exactly 0. And in a circuit, even if you don't put a resistor in there, even the wires that you connect things with have a little bit of resistance, and so resistance is never actually 0. So as a result, lambda is always positive in applications, in actual physical systems. So when we go to solve this differential equation, right, the first thing that we'll do is we will find y sub c, and to find the complementary solution y sub c, we'll write down the characteristic equation for the associated homogeneous equation. So let me use r for the variable in that equation. So r squared plus 2 lambda r plus omega squared equals 0. And when we write down solutions to this, right, we get r equals minus lambda plus or minus some square root here. Now this square root part over here, it might be imaginary or it might be real, but either way, the real part of r is always less than 0. So we've looked at this before. No matter what this square root turns out to be, real or imaginary, if you sort of carefully analyze whether this sum could ever come out to be positive, it can't. When lambda is positive, this is always, the real part of this is always negative. So there are a couple cases, either, well, there are 3 cases. In the 2 real root case, our complementary solution will look like some constant times e to some negative power times t plus some other constant times e to some other negative power times t. Right? In the 1 real root case, this complementary solution will look like some constant times e to some negative power times t plus c2 times t e to that same negative power times t. And in the complex root case, where your roots to the characteristic equation are complex conjugates, your solutions are going to look like y sub c is going to be e to the minus lambda t times some combination of sines and cosines. Like this. Okay, so in all of these cases, when you solve when you find a particular solution to the original differential equation, right, your full solution is going to be your particular solution plus this complementary solution. And in all of these cases, no matter which case we're in, as t goes to infinity, the complementary solution goes to 0. Right? In the 2 real root case, because these exponents, these coefficients in our exponents are negative, both of these exponentials are exponential decay and not growth. In the 1 real root case, this first term is exponential growth or exponential decay. The second term, t goes to infinity, but e to the negative any constant times t goes to 0 faster than t goes to infinity, so even this goes to 0. It's not quite exponential decay, it's slightly sub-exponential, but it does go to 0. And in the complex root case, this sinusoidal part, it has some maximum amplitude, but it's being multiplied by something that's decaying exponentially. And again, it's decaying rather than growing exponentially because this coefficient in the exponent is negative. So in each of these 3 cases, the complementary solution goes to 0. So the complementary solution, because it sort of, once you set up your system and let it run, since the complementary solution eventually gets really, really small, this often gets called the transient. Okay, and what determines the transient is, well, first of all, the system, but also, right, the transient, since the transient is the complementary solution, the transient has these unknown coefficients in it. And those coefficients are determined by the initial conditions. So the transient is determined by initial conditions together with the system. The particular solution, on the other hand, we will see in typical examples that the particular solution tends to last forever. So the particular solution usually doesn't go to 0 as time goes to infinity. And so it's called the steady state because it lasts forever. And what determines the steady state, right, if you think back to examples where we've found a particular solution, the initial conditions have never come into finding the particular solutions. The initial condition only determines the complementary solution. So for the steady state, the initial conditions don't really matter at all. It's just the system together with the forcing function f of t that determines the steady state. So for all linear systems, all second-order linear systems of this kind, there's this sort of nice separation in your solution. There's the complementary solution that's determined by initial conditions, and there's the particular solution that's determined by the forcing. The initial conditions don't influence the particular solution, and the forcing function doesn't influence the complementary solution.